Hi all, I'm Prathamesh. I'll be talking about information constraint optimization. This is joint work with Jaydev Acharya, Clement Canon, and Himanshu Tyagi. So by information constraint optimization, I mean optimization scenarios which appear in federated learning setup where gradients from the mobile devices to the server need to be processed for various reasons. It could be to save the uplink bits from the mobile devices to the server, in which case they are quantized. It could be to because the devices need some more privacy guarantees, in which case they would employ a LDP mechanism to privatize their gradient updates and then send them to the server. And what we ask in this study is at various iterations of your training, machine learning model training at the server, if the processing mechanism you use to process the gradients, if that is adaptively changed, does that help you to train your models faster? Yeah. So let me formally describe the setup. So before I describe our setup, let me describe the classical query complexity setup of for optimization. So we have a algorithm pi which wants to minimize an unknown function f using access to a first order oracle. And the algorithm queries the first order oracle at some point xt at iteration t. Upon receiving this query, the oracle gives back a gradient estimate to the algorithm, and the algorithm updates its point xt. And the typical question we are interested in is for a class of functions and some noise assumptions on the oracle, what is the best possible convergence rate you can get, and which is the algorithm which gets you that convergence rate. So this is the classical setup. Now let me describe our setup for information constraint optimization. So I guess the big change with respect to the classical setup is this blue box here, and it's called a channel. It's essentially a bunch of distributions, different distributions for different distributions corresponding to different gradient values. So, and what the algorithm does is at every iteration, along with querying a point xt, it will also tell the oracle, hey, use this channel wt at iteration t. The oracle outputs the subgradient estimate g hat xt. But then now this subgradient estimate is not directly available to the algorithm. This passes through the channel wt, and only the output of the channel is available to the algorithm. So the output y, so essentially we get to choose the distribution with which the output y will be generated given the input g hat xt, but we don't get to see g hat xt. Of course, this reduces to the classical setup if you're allowed the identity channel. And what we want to answer in such a setup is, does adaptive gradient coding help? Meaning, if I'm allowed to change, let's say at time t, the algorithm would have some information of what the gradients would likely to be based on previous iteration. So does changing the channel to be used at time t based on all the previous information it has received help in any way to optimize faster? Yeah. And to map it back to the federated learning example we saw at the start, you can think of this as some sort of one worker scenario where at each iteration there's only one worker communicating with the center, which in this case is the algorithm. Yeah. So let me describe what information constraints we look at in the paper. The first one is local differential privacy. And this is the precise condition. It just says that given the output, you cannot precisely tell what input was used to generate it. The second one is communication constraints, which states that the output can be represented using R bits. And the final one is the random coordinate descent constraint, which essentially states that given that, let's say this essentially models computational constraints. Suppose you cannot compute the entire gradient estimate, but maybe can just compute one coordinate of the gradient. So this is essentially that condition. You get to just see one coordinate. You can randomly sample which coordinate you want to see, and that's allowed. So you get to see that coordinate and the index which you sample. So these are the privacy constraints. What is the function class we look at? So our domain X will be the Euclidean set of diameter D, and our function and oracle class is described as follows. Our function f is convex. The oracle O, upon receiving a query X, always outputs a unbiased subgradient estimate of the function at that query, and the subgradient estimates L2 norm is almost surely bounded. Notice that this condition says something about the subgradient of the function at that point, and therefore the function itself, but also the noise added by the oracle. And for such a class, we'll characterize the following min-max gap to optimality. So let's recall the classical result when there were no information constraint. Given T queries, we would converge at the rate 1 by root T. Our gap to optimality, expected gap to optimality given T queries is 1 by root T. Yeah. So what is the blow up because of the information constraints? So under a privacy constraint, you have a blow up by a factor of square root D by epsilon square. Under communication constraint, you have a blow up of a factor of square root D by R. And under random coordinate distance constraints, or maybe you can think of them as a very stringent computational constraint, you have a blow up of a factor of square root D. And perhaps it's easier to see that this thing is tight for random coordinate descent like constraint, because you could think of a uniform sampling mechanism which would add just sample one coordinate of a gradient, and that would blow up the variance by a factor D. So the square root of the variance would be blown up by factor square root D. So and essentially we get a bound matching this lower bound. And this is done by uniform sampling. So the sampling mechanism remains the same throughout the T iterations. In other words, it's non-adaptive. And yet we achieve this lower bound which holds for adaptive protocol. In fact, all these lower bounds are tight, firstly, and they are all achieved by non-adaptive gradient coding. So you can just fix your privacy mechanism or your quantizer, or in this case, your sampling mechanism for T iterations, and that mechanism along with some optimal mechanism along with projected stochastic gradient descent will achieve this lower bounds. So how do we go about proving this? So the takeaway here is, before I go to the proof, is that adaptive gradient coding does not help for this class at least. So the proof idea is similar to previous works or previous lower bounds in this literature, in particular to Alek Agarwal's 2012 paper. And the idea is as follows. My domain will be a hypercube centered at 0. And I have this, this is a well-known identified bottleneck for convex class. This is a bunch of linear functions, 2 raised to D linear functions. And our oracle outputs a Bernoulli product distribution which is an unbiased estimator of this parameter V, which scaled some scaled version of the unbiased estimate of this parameter V, which is essentially the subgradient. And the idea behind the proof is that notice that each of these 2 raised to D functions have their optimal solution as one of the corner points of this hypercube. So if you're able to optimize this function well enough, any algorithm which is able to optimize this function well enough should be able to identify, should be able to be close enough to the corner point. But if you're able to be close enough to the corner point, you would also know this, you should also be able to estimate this parameter V. but there is an inherent bottleneck in estimating this parameter V, so optimizing the function should also be difficult. So, and this is all captured in this bound. The key part of this bound is the following quantity here. The fact that we could get a coordinate-wise mutual information term as opposed to the standard mutual information term which you see in previous works meant that so this is a smaller quantity and it's easier to bound. We're not so sure if a similar bound could be proven for all sort of distributions for this slightly bigger term. So this essentially made the proof go through for adaptive protocols. And once we have this term, we could use a result derived by my co-authors and Jitin on which was for interactive high dimensional estimation under information constraint, which handled bounding such kind of terms. So this bound along with a bound on the mutual information from this paper kind of completes the proof for convex class. So what I haven't described so far is the other classes of functions we also handle. So one such class is strongly convex functions, and perhaps this is one of the earlier works to derive lower bounds under information constraints for the strongly convex class. So here the bottlenecks are of the form are of quadratic nature, and in such a setting, the gradients are no longer independent of the queried point. This means if you repeat the recipe of the proof, which I just described, and get to the mutual information term, the mutual information between V and the coded sequence of gradients, which is the YTs, they'll have that mutual information would not be very easy to bound. But and essentially we need upper bounds on mutual information which hold for adaptive protocols, even prove lower bounds for non-adaptive gradient processing algorithms. And the bottom line here again was that even here, our lower bounds which hold for adaptive protocols were achieved by non-adaptive gradient coding. So adaptive gradient coding does not help even here. So is there actually a class of optimization problem where adaptivity helps? It turns out there is. And here's one such example. So my domain will be hypercube centered at 0, and I'm trying to minimize. It's a simple L2 minimization problem where the function is parameterized by this parameter V, which is what we call S block sparse. So think of a d-dimensional vector to describe what S block sparse means. Think of a d-dimensional vector divided into chunks of S coordinates, chunks of S successive coordinates. They'll be d by S such different blocks. S block sparse vector will only have one such block to have non-zero values, and all the coordinates within that one such block would have the same absolute value. Yeah, our oracle is outputs the following quantity 2xt minus 2zt, where zt is an unbiased estimate of our parameter v, and we'll study this problem under the random coordinate descent information constraint, meaning at every iteration you just get to see one coordinate of your gradient estimates. So here's the lower bound for non-adaptive protocol. This lower bound states that, let's say if your d raised to 1 by 3 block sparse where s is, meaning s is d raised to 1 by 3, lower bound states that the gap to optimality is super linear in d, but we show an existence of an adaptive protocol where it's just roughly linear in d. So there's a significant gap between the performance of an adaptive protocol over a non-adaptive protocol. So adaptivity does help in this case. And what is this algorithm? So given a budget of t queries, we use our first t by 2 queries to find the non-sparse block, and then use the last t by 2 queries to just form good estimates of all the coordinates within the chosen block. Yeah. So in summary, adaptive coding does not help for standard optimization problems. However, for structured optimization problems, adaptive coding doesn't. Also, adaptive techniques you are useful in deriving lower bounds for for non for proving lower bounds, for even proving non-adaptive lower bounds for information constraint optimizations. Yeah. So that concludes the talk. Thank you.